Hello, in this video let's continue the discussion of Verilog syntaxes. So now let's discuss sequential logic, and let's look at a very simple piece of sequential logic. Again here, since we're not worried too much about the structural definition of hardware, we're looking at a behavioral definition. So let's look at 8-bit register, if you will. Alright? What that means is essentially you have 8 flip-flops connected in parallel. So you have one clock signal that goes into all the 8 flip-flops. There is an 8-bit input word and an 8-bit output word. And when the clock goes high, because this is a positive edged flip-flop, the output takes up all the values that are given at the input, right? So that's the meaning of this component. So now when I want to code this up in Verilog as a behavioral model, again I start off with defining the module and defining the signals into the module. So I have an input logic signal, which is the clock signal. I have another input signal, which is the input word, and I have an output signal, which is the signal Q. And all the input and output signals are both 8-bit signals. So I use the keyword known as always underscore FF, within brackets positive edge of the clock, and when that is true, D gets mapped onto Q, end of module. So the key statement here when you're defining sequential logic is this always, right? So the always keyword tells Verilog to execute whatever follows after that statement whenever the conditions within the bracket or whenever the event in the bracket occurs. So in this case, when I say at positive edge, it indicates the rising edge of the clock. So always FF will execute every time Verilog encounters the positive edge of the clock. Now, what is written into the bracket is known as the sensitivity list. So we'll look at further examples in this video where you can use the same concept of always for latches. You can also use it for combinational logic. So again, what the always statement does is it looks at this list of statements or signals inside the brackets, which is known as the sensitivity list, and based on the values of those events or list variables, whatever is after the always statement gets executed. Now what we've used within this loop is Q gets the value of D. Now using this symbol less than equal to is known as a non-blocking assignment. So further on in the video I'll talk a little bit about blocking versus non-blocking. So I want to point out that here what we've used is a non-blocking assignment for the sequential logic. Now to reduce errors, because this concept of always can be applied for multiple circuit types, 3 types of always statements are available in SystemVerilog. One is the always underscore FF, one is the always underscore latch, and one is the always underscore comp, right? And they're used specifically when you're doing flip-flops, latches, or combinatorial circuits. You can switch one for the other, it's going to be implemented fine, but this helps you write a code that is easier for you to understand. So it's recommended that you use the underscore FF, underscore latch, and underscore comp to keep your code readable and debuggable. Now let's look at how do you modify the code before if I want to introduce a reset signal into the clock, into the register. So again, now this reset signal, as we've looked in digital design, we can think of this either as a synchronous or as an asynchronous reset. What I mean by that is, in an asynchronous reset, whenever reset goes high, independent of whether the clock is in or out, the register gets zeroed in, right? On the other hand, when you think about a synchronous reset assumes that the reset is in sync with the clock. And so then what happens in that case is reset, only when reset comes, the value of reset after the clock edge has come in is taken in, and then the state of the register is evaluated. So fundamentally, the way the register works, the way the hardware would be synthesized would be vastly different depending on whether you assume an asynchronous or a synchronous reset. But again, here, if I want to describe the behavioral model of this circuit, then it becomes very simple compared to the hardware, right? So let's look at the asynchronous reset first, which is the simpler case. So in that case, what you have basically an 8-bit, let's say a flip-flop with an asynchronous reset. So like before, you have the two input signals, clock and input D. In addition, you have this input, which is the single bit reset signal, and then you have an output 8-bit word. And so the way you define this here is always underscore FF at the positive edge of the clock and at the positive edge of reset. So when reset goes high or when the clock goes high, evaluate what's after it. And so once the reset changes once, so remember the positive edge of reset when it goes from 0 to 1. After that, if reset, now this if statement like C looks at the value of what's in the bracket. So if reset is high, in that case Q is set to all zeros, else Q follows D. So it enters what is inside here at the positive edges of both these circuits, positive edge of the clock and positive edge of reset, and depending on the value of reset, it either resets the register or it just functions like the regular register. Now if I want to do the same thing in a synchronous fashion, again, the code will be slightly different. Remember, the hardware is going to be very different in this case. But if you look at the synchronous reset, there it enters only during the clock edge, right? So this the assumption is when using synchronous reset is you're assuming that the reset is going to happen in sync with the clock. So when the clock edge comes in, then depending on whatever is the value at the reset pin, the register either gets reset to 0 or it follows a regular register. Now let's bring in another signal, which is the enable signal. So let's assume that we now want to add in another signal, the enable signal. And the enable signal ensures that only when enable is high does this piece of hardware function like a register. So it's kind of the gating for this piece of hardware. So again, there you see that it's quoted in as an input signal. So you have an input logic enable here. And so always at FF, again, this is to implement the synchronous logic, the flip-flop. At the positive edge, you first check if reset is on. If reset is high, then reset the output to 0. Else, you check for value of enable. Only if enable is high, you let the register function as normal. Else, Q does not change and Q remains whatever it was prior to it. And whatever is the value of D does not get reflected onto Q if enable is 0. Right? So you can think of, you keep adding inputs, you change the logic within the flip-flop. Remember, all these are behavioral models. The way they're going to be synthesized is going to be different depending on the kind of reset, for example, you've used and what you have. Now let's assume that we want to, so you can extend this program to implement, say, a piece of STA, for example, right? When you want to do a bunch of registers with logic in between, that can also be implemented. So here I've taken a very simple case where I have one flip-flop and another flip-flop, and I'm passing the data from one flip-flop to another flip-flop, right? So here, if you look at the input signal, you have an input signal which is D and a clock signal, and an output Q which comes out of the second flip-flop. What is happening inside this N1 signal is an internal signal to the flip-flop or to the circuit. You don't see it outside. Right? So this, for example, is a very simple synchronizer, right? So this ensures that Q is synchronized to the clock once it comes out. So how do you load this up again? It has an input clock and the input D signal and output Q signal. I define an internal variable within the module, which is my N1. Now again, at the positive edge of the clock, I'm doing two non-blocking assignments now. The first thing I'm doing is I'm letting N1 follow D and I'm letting Q follow D. Now because these are non-blocking assignments, what's going to happen is both these are going to be done at the same time. They're not necessarily going to be executed sequentially, and that's the basic difference between a blocking and a non-blocking assignment, right? So in this case, what's going to happen at the same time, both these statements get evaluated. So whatever was the value of N1 gets transferred to Q at the clock edge, and whatever was the value of D gets transferred to N1 at the clock edge. Now we've looked at registers. If you look at latches are nothing but level sensitive sequential elements. So in that case, I have a clock, and so this latch is transparent when clock is high, else the latch is opaque. So when the latch is transparent, whatever is the change in D gets reflected on Q, right? And so here again, I have two input signals, the clock and the logic input D, and an output word which is Q. Now this, here I use the keyword always latch. So what always latch does is, it is going to look at both the inputs, clock and D, and it's going to evaluate it whenever both of these change, right? So it's like, remember in combinatorial logic, when we use the assign statement, whenever the input changes, the output would automatically change. So the same thing happens here. This always underscore latch basically is going to be evaluated every time the input signals change. And so at that time, what's it going to do? It's going to see if clock is high or not. If clock is high, Q follows D, else Q is not changed because of D. So you can also think of this always latch as something like always at clock comma D. That is, whatever follows the always latch is going to be evaluated every time the inputs change. Now, this same logic of a latch can be extended to combinatorial. So I can use this always statement also for combinatorial logic. Now, one would think, why would you do that? Because you have your assignment statements. And so for simple logic, generally it doesn't make sense to use always. But always helps a lot, especially when you're doing complicated logic, again for a behavioral case, right? And we look at one example. So here's a very simple example. Suppose I want to generate a bank of inverters. So here I have an input 8-bit word and output 8-bit word, and I want to ensure that the output word is the complement of the input word. So what I do is I use the keyword always underscore comb, and I say y is the complement of x. So this always underscore comb is similar to saying always at star. Star, that is, whenever the input, any signal at the input changes, this whatever follows the always statement is going to be executed, right? And so anytime any input signal changes, whatever follows changes. So it's like combinatorial logic, because once the inputs change, the outputs are going to change according to the logic. Now here, if you see within the combinatorial logic, I've used a y equal to. Now this equal to is known as a blocking assignment, right? In contrast to the less than equal to symbol which we have used for non-blocking. And as I mentioned before, blocking assignments are evaluated in the order they appear in the code, right? So if you had multiple changes, this statement is going to be evaluated, after which the statement is evaluated. So if you're using y somewhere later, you better have y used as a blocking assignment, because then the y value gets updated, and then that updated value is then going to go into the next statement. If you use non-blocking, they're all going to be evaluated at the same time. And so in always statement, we'll see that whenever you're doing combinatorial logic using always, we'll always use the blocking assignments. We will not use non-blocking assignments typically for combinatorial logic. And if you want to use an assign statement, assign statements are generally used outside the always block. So the way Verilog compiles, you want to ensure that when you're using an always block for combinatorial logic, you want to use it with the blocking statement inside. So let's look at a case of a slightly complicated combinatorial logic, right? So suppose I want to design a 7-segment decoder. So what a 7-segment decoder does is it has a 4-input. It takes in 4 inputs and provides outputs to 7 LEDs, which are used for displays. Most of you would have used it when you built any boards or simple circuits. Now, when you want to code this up, using a statement like an always with a case makes it very easy. You don't have to worry about hardware, and it is a very compact and easy code to model what's happening within the circuit. So again, I define a module which has an input logic, which is num. So num is a 4-bit logic. Remember, the 7-segment decoder takes in a BCD number and gives out 7 outputs which are connected to the 7 LEDs, right? So my output logic is a 7-bit word. So now always at comb, which means this circuit is going to work whenever the input pins change. And now I define a case, right? So what's going to happen is based on what the value of the input pin number is, depending on its values, LED is going to be assigned to different numbers. So you see that as I walk from case 0, 1, 2, 3, 4 all the way to case 9, right? I am assigning the LED signal to the corresponding signal so as to light up those specific LEDs. And in a case, you normally always, it's a good idea to have a default statement. So what this default statement does is, in case the input pins do not encounter any one of these cases, the default statement tells it what to do. So in this case, I'm saying that if it's not a valid BCD number, then don't light up. So the LEDs all go to 0 when the input is not a BCD number. So if you were to code this up, say in a proper hardware using gates, etc., this would be a longer code. But if you want to use this in a larger architecture, this makes it very simple to code up a 7-segment decoder. So as I mentioned, this always statement comes in handy when you want to deal with combinatorial logic, which is more complicated than simply a bunch of gates. Now remember that when using case, it's always recommended that the case statement sits inside an always statement, right? Now similar to the case statement, another powerful statement you can use is the if statement, like how we saw in the flip-flop and the latches case. So again here, suppose I want to do a priority encoder. So if you remember what a priority encoder was, a priority encoder essentially assigns the outputs high depending on the values of MSB, so an LSB, right? For example, suppose this is an input A, which is a 4-bit input, and the output D, which is a 4-bit output. If the MSB of A is 1, then independent of what the other values or bits in A are going to be, D is always going to be assigned in such a way that it's going to be assigned to 1000, right? And so basically when A of 3, that is when the MSB of A is 1, the rest of the bits of A become a don't care condition. So one easy way to code this up would be, again, use an always statement and then have an if statement where you look at the value of A of 3. So if A of 3, then D is given this 1000, else you look at the value of A2. So if A3 is 0, then you go to the next if statement and look at the value of 2, right? And if A2 is 1, then you assign 0, 1, 0, 0, and so on and so forth. So this is a very simple way to do a priority encoder. As I mentioned, this A3, when the first one is high, the rest of them are essentially don't cares. So I can also code up don't cares in Verilog, and the way you would code up don't care. So if I'm going to code up the same circuit using the don't care conditions, I use what is known as a case Z. Instead of case, I use a case Z. Right, and so here I'm not using an if statement, I'm using a case statement where I'm saying that depending on the value of A, now when I'm calling A, I'm saying that I want to look at the case when the MSB is 1, but I don't care about the other bits. So I would put in that case as 1 question mark question mark question mark. So this question mark stands for a don't care. So all values of A where the MSB is 1 are going to default to this first statement, right? So which is exactly what we did here. So independent of what's happening for A2, A1 or A0, if A3 is 1, then you're going to assign 1000 to the output word, right? So both these are essentially the same circuit, it's just different ways of encoding. You can either use an if statement here to code up this piece of hardware, or you can use don't care conditions, right? And the way you use don't care, as I said, is using the question mark. So a quick reminder on the blocking and non-blocking. So whenever you have to do any kind of sequential logic, flip-flops, etc., use non-blocking assignments, because in those cases the flip-flops do not have a sequential assignment of bits, if you will, right? So when the clock comes in, all the dominoes, if you will flip. And so therefore in that case you want to ensure that you're using non-blocking assignments and you don't have assignments which are order specific. When you want to do combinatorial logic, very simple logic, you want to use the assignment statement, which is the equal to symbol. And when you want to use To model complicated logic, always use the always comb in combination and blocking assignments to model complicated logic. And finally, ensure that you don't make more than one assignment to the same signal within an always statement, else it's going to throw up an error or give you errors in the output. So make sure that whenever you're using the always, one signal is assigned only once during the always function. Now let's look at a quick example of a finite state machine. So let's remember what a finite state machine is. So finite state machines can be of two types, a Moore machine or a Mealy machine. A finite state machine essentially has a clock or a register, right? And this clock is essentially storing the state of the machine, if you will. In the Moore case, the state dictates what the output of the machine are going to be. So you have some sort of logic which converts what the state variable is into an output signal. And similarly, you have some logic here which takes in inputs and the current state, and using some logic gets it to the next state. So if you think about a finite state machine, your finite state machine should have one, if I'm going to think about coding it up, I'm going to have one part of the code which is going to be nothing but a register which is storing the state variable. I'll have some part of the code which is going to be implementing the output logic, and another part of the code which is going to be implementing the next state logic. So that's essentially, if you look at the way you would implement an FSM based on what you've learned so far, in that the code has essentially three important parts: the register part, the output logic part, and the next state logic part. In the Mealy machine, as you all know, the difference is only that the outputs are not only determined by the state but also determined by the inputs. So in that case, your input not only goes into the next state logic, it is also fed into the output logic segment. So but for in terms of Verilog, the codes are roughly going to be same. Again, three parts. You're going to have a register, you're going to have an output logic, and you're going to have a next state logic. Now let's look at a simple example, which is a divide by n counter or a divide by 3 counter. That is, I have a clock which has a certain frequency and I want to generate an output whose frequency is, say, 1/3 the frequency of the clock, right? So if I want to think about a finite state machine of this, I want every time the clock comes in, right, I want the machine to count, right? And 1, 2, 3, the fourth time again it's going to come out again. So the way I'd code up this FSM would be using three states, right? S0, S1 and S2, right? Every time a clock comes in, I'm going to push S0 into S1, S1 into S2 and S2 back into S0. So it goes through multiple states, and what's going to happen is the output is going to be high only during when it's in state, say, S0. So this is the Moore implementation of this particular FSM. And like every time when you do a good logic, you want to ensure you have a reset signal so as to prevent any spurious interaction with inputs. So this reset is going to ensure that you start off with a 0, for example. So in normal cases, the way you would set up the logic for this is you'll define the state variable. Since I have three states, I'll define it as a 2-bit number. So I'll call S0, 0, 0, S1, 0, 1, S2, 1, 0, where S1, S0 defines the state. And then I'll create the transition table for the FSM, which consists of the current state, the next state, and the output. Right? Again, this is a Moore machine, right? And so this is if my current state is 0, 0, my next state has to become 0, 1. And during this S0 state, my output is 1. The next time the clock comes in, my 0, 1 moves to 1, 0, output goes to 0. Again, the clock comes in, it goes from 1, 0 to 0, 0, output stays 0. And the output again becomes 1 when the clock comes in and it's in state 0 and it goes to state 1. Right? So again, if you were to do this, you will get the logic expressions for S1 bar, that is the next state logic, to be S1 bar S0, S0 prime to be S1 bar S0 prime, and the output signal to be S1 bar S0 bar. Right? So this is how you would do an hardware implementation of the FSM. Now we're doing behavioral modeling, so Verilog makes our job slightly easier. So the way we would code up this in Verilog would be, again, we are coding up an FSM, which is a divide by 3 counter. It has two input signals, a clock and the reset, and it has one output signal, which is the out variable. If you look at the code roughly falls into three, as I said, three parts. There is a clock or a register which is controlling a state variable. You have a logic piece which is telling you how the states transition, so from the current state to the next state. And then you have a part of the code which is telling you what the output should look like. So the first step in implementing FSM is using this definition, which is the defining the state type. So here I'm using a 10 or a 2-bit logic to define the state. I'm calling out the three states S0, S1, S2, and the state type is a 2-bit state, and it has to go to the next state. So these statements are basically telling Verilog that you're implementing in FSM. Now if you look at this carefully, I've not really specified how to code the states. By default, Verilog is going to take this as a binary encoding, so it's going to give 0, 0, 0, 1, 1, 0. Now the first step here again is you first have the flip-flop which you're implementing, which says that at the positive edge of the clock, if the reset is not high, then state is replaced by the next state, right? So this is the one which is doing the transition between the current state and the next state. Now, how does that transition occur? How do you decide what is the next state? Comes in the second part of the code, which is your combinatorial block, which says that always at comb case of state. So it takes up the state as a case. When the case is S0, because you defined the three states to be S0, S1, S2. When it is S0, the next state is S1. When it's S1, S2 is written to next state, and so on and so forth. And like always, the case statement has a default, which says that if there is by chance, if those bits have gone to 1, 1, say 1, 1 is an invalid state encoding in this case. But if it does go there, we want to ensure that during the next clock, it comes to valid state. So this is a good way of coding FSM, as you've seen in some of the lectures of digital design. You normally want to ensure that any freak states are brought back into the state machine. And finally, you have a output logic which says that only when the state is S0, you want the output to be high. So in this case, Y should be the output. So I would say assign out is equal to state when state is S0. And so if you look at this is the key statement in the FSM definition. So it defines the state type to be a 2-bit logical value with 3 possibilities with a state and a next state signal. So these, it becomes clear. So if I want to do multiple states, you need to add on to this number here, right? And the binary values are typically assigned by default. If you want to be specific, if you want to change the way it's assigned, you can also call out the specific assignment. So this statement here, I can write it very clearly as typed of enum logic of 10, and I'll call out S0 to be 00, S1 to be 01, and S2 to be 10. So I can do this specifically, but what the statement is doing is by default assigning it in this fashion, right? And then finally the output is high when the state is 0. Okay? So I hope you've gotten an idea as to how to code up sequential logic in this case. What we'll do in the next video is we'll look at how to parameterize code in Verilog and how to write test benches